Today we will be analyzing the kinetics of a side-foot soccer pass using Newton's three laws of motions, forces, and torques. Newton's first law of motion is the law of inertia, and it states that a body will maintain in a state of rest or constant velocity unless acted on by an external force that changes the state of motion. This law relates to a soccer kick, as the soccer ball will remain at rest until the kicking leg accelerates downward during the acceleration phase to create an impact and move the ball along the ground. In this video, the external force of gravity and friction is the reason why the ball will eventually stop. The ball can't go on forever. However, the distance the ball travels will depend on the velocity and power it is impacted with until the friction of the turf and weight stop the ball from going. Friction is a force acting over the area of contact between two surfaces. Its direction is opposite of motion or motion tendency, and the friction's magnitude is the product of the coefficient of friction and the normal force. Newton's second law of motion is the law of acceleration, and it states a force applied to a body causes acceleration of that body. This law relates to the soccer kick, as the soccer ball is going to experience a constant velocity until we place an external force changing the momentum in either positive or negative magnitude. Momentum is defined as a quantity of motion possessed by a body, and it is measured as a product of a body's mass and velocity. In a real-life scenario of a soccer pass, as seen in the video below, the ball will be stopped completely by another partner, or if practicing continuous soccer passes where the ball is not stopped, the momentum of the ball will change as the velocity of the ball increases and gains more momentum. According to R. Kawamoto et al. 2007, good transfer of momentum from the kicking leg to the ball is also important to use efficiently to increase the ball's speed. The coefficient of restitution is a number that serves as an index of elasticity for colliding bodies. According to Kellis and Caddis et al. 2007, past literature has suggested that a change in the coefficient of restitution from 0.5 to 0.6 would lead to a 10% rise in ball speed. The coefficient depends on mechanical properties of the ball, the shoe, the ankle, and foot upon impact. The less deformation by the foot, the higher the coefficient. The amount of deformation is dependent of the effectiveness of the foot and leg. According to Dorsch et al. 2007, a small difference in extension and stiffness of the ankle joints would probably alter the mechanics of the collision, thereby causing the coefficients of restitution to differ between kicks. They also found that the angular velocity of the shank was caused by moments of force acting on the segment. These moments originated from the muscle forces on the segment and from the joint reaction forces. Therefore, the linear speeds of the foot originated from the torque of the leg. Torque is the rotary effect of a force about an axis of rotation. It is measured as a product of force and the force's moment arm. The force's moment arm is the shortest perpendicular distance between a force's line of action and an axis of rotation. The product of muscle tension and muscle moment arm produces a torque at the joint crossed by the muscle. And according to R. Kawamoto et al. 2007, the critical knee factor to increase the speed of the kicking leg is a hip flexion torque during the early stage of the kicking phase. Rahama et al. 2005 suggests that the difference in muscle strength between the dominant and non-dominant leg could be explained by the fact that the knee of the plant leg is flexed during kicking, and the plant's flexor muscles are required to stabilize the knee joint, support the weight of the body, and resist the reaction of torque produced by the opposite limb. ACL sprains are the most common injury that happens in the non-dominant leg when it is planted during the approach phase through the follow-through. This occurs because the knee is compressed as it is supporting the weight of the body and resists the torque of the dominant leg.